Good morning, everyone. I am Dr. Darshika Vaningaratna. I am the lecturer for your Properties of Materials course. Right? So, I will give you a brief introduction about myself. Right? I am currently a lecturer in the Department of Civil and Environmental Engineering in Faculty of Technology. I am a graduate from Faculty of Engineering, University of Peradeniya, right? Then I obtained my PhD in Nanyang Technological University in Singapore, right? I am specialized in uh, civil engineering field, right? So actually, it's better if we could meet face to face, like our usual lectures. But unfortunately, with the current situation, the only remaining option is to do the online lectures. Actually, I was planning to do this as an online Zoom lecture, so at least I could have a discussion with you. But unfortunately, I am having uh, shifting duties tomorrow morning, so I'm not sure whether I will have a proper environment to conduct a online or Zoom lecture. So I will give this lecture as a pre-recorded lecture, right? And also I will upload the this lecture slides in PDF format to the LMS. So if you had any lectures in the previous week, I know now you are somewhat familiar with how to use LMS and how to download the that recordings, that means lecture materials from there, right? So if you have any question regarding this LMSO, any course related question, you can email me, right? This is my email address, darshika@sjp.ac.lk. So you can email me at any time. And also you have the facility to send messages through LMS also. Even you send messages through LMS without typing a separate email, I will receive those messages also, right? So if you have any question regarding the subject or any other matter, you can email me at any time, right? So I think you are from different areas, right? It means from different schools. So anyway, you are engineering technology students, right? So therefore, I hope that you all have already received a certain knowledge about this little bit of knowledge about chemistry, little bit knowledge about physics and maths already in your A levels, right? Because for this course, that means for the properties of materials course, you may need your knowledge about chemistry, physics, and maths, right? So actually, this was a course that was uh, in second semester, first year, second semester, but from this year onwards, they have shifted this course to the first semester, right? So you will have that chemistry course, a physics course, and a maths in the ongoing semester. But uh, if you at any place in this course, if you need the those basic knowledge, I will give you the relevant that knowledge part only, right? Then you can conveniently follow the course, right? So I am not adding this as a continuous video. I will break this into maybe for three recordings. Then I will upload it as one, two, three, like three recordings. So you have to follow the order when you watch the video so that you can properly follow the order of the lecture, right? Because I'm doing that like then. I heard from some students that it takes a lot data to download a large file, so they prefer to download small video clips and combine it later, right? So I will be adding maximum around 3 to 4 recordings per lecture, right? Okay. if we move to this properties of material course, last time I uploaded the I have uploaded the syllabus, right? The syllabus I have already uploaded, so you could, I hope that you will be able to see the content of this course. Basically, we are going to learn properties of material, the mechanical properties, then electrical properties, then the properties of metals, properties of polymers, properties of composites, likewise. Uh, because here you are first year students. After the first year, you will be separated into several fields. For example, some people will follow uh, construction and building services course. Some people will follow energy and environment course, right? Some people will follow automobile. Some people will follow mechatronics. So likewise, you will go for different areas, right? So here in this course, materials we discuss are not specific to only particular field, but in commonly the most of the common materials you can find in any field we discuss in here, the properties, right? So this is a 2 credit course. So this time the evaluation criteria will be a bit different. Last time we had around 70 to 80% marks to be covered during the end semester examination, 20 to 30 marks to cover from assignments, quizzes, and practicals. But as we are conducting online lectures, I think most of the higher percentage of your end semester, your exam marks will be covered by the assignments, quizzes, like that, right? So basically, I am planning to give you around 4 to 6 assignments, right? To be covered to cover around 60 to 70% of final marks, right? So I'm not sure whether we can do the practicals this year because you cannot physically present in the university to to do the practical. So I will try to upload maybe the videos for you to demonstrate how we do such practicals, right? Basically, for the previous badges, we did 2 practicals, right? One is the tensile test, other one is the hardness test. So I will try to at least to upload those demonstration videos to you to understand, right? So let's move to the course. Okay, let's uh, let's uh, let's move to our course. Right. So this is the introduction. Let me ask you 2 questions. What are materials, and why we should study about properties of materials? Right. So what are materials? We all use different products, different equipments, right? Different things in our day-to-day life. Sorry. Right? So all those things are made out of materials, but from different materials. For example, your house may have constructed from cement sand blocks or bricks, right? Like that. Then, if you take if you have a vehicle in your family, then for different parts in the vehicle, they have used different materials, right? For some part, it's a metal. For some part, it's a metal, but not the same metal. Right? For some part, some polymers. For some parts, some plastics, glass. Right? So we have different materials, metals, glass, polymers. Right? Then the composite materials we will learn later. Right? Those are all materials. Right? So why we should study about properties of materials? Because we cannot use a single material for every requirement. Right? Based on the properties of material, we have to decide for what purpose we are going to use this material. Right? That's the basically why we try to learn the properties of materials. Right? We should know the properties in order to use it for a particular application. Right? So that's it. Right? So if it is a material, you know, every material is made out of a one element or a group of elements. Right? For example, if say it is iron, right? The iron we can describe using its atomic structure. Right? You know, if it is aluminium, it has different atomic structure. So the properties of aluminium and iron are different. Why? They have different atomic structure. Right? Because of the variations of the atomic structure, the properties of materials can change. And also the way the process certain material, these properties can change. Right? For example, when they process the material, the temperature condition, the air environment, right? Those things or the impurities you add, those things can change the original properties of a material. Right? So let's say we are always try to find high performance material, right? In order to create different smart materials, you should clearly know the structure of material, that means the atomic structure, and the how, according to the processing condition, how the properties change. If you know those two things very clearly, you can think about changing certain conditions of processing, right? Or you can think of combining one element with some other elements to make very high performance smart materials. Right? So materials we are not only, you can find in everywhere. For example, you know that for the water purification, right? People are trying so many materials for the purification of water, right? In that case, they try to change the properties of one material bit by bit by identifying the factors that affect those properties of the material, right? So, however, the main target of this course is not to teach you how to change the properties of material, but to give you the idea about the basic properties of certain materials. Okay, right? So, what are important considerations when screening material for a specific application? Right? So, if you have a certain application, for example, you need to create a design a machine shaft, for example, right? So how you think of candidate materials for that shaft? What you expect from the selected material to have depending on your application. So you should think about, should it be stiff, or it should be strong, or ductile, or all the properties should be there, or like that, right? So with that shaft subjected to high stresses, sudden intense forces, high temperatures, cyclic stresses, corrosive conditions, whether it will expose. If it expose, so your selected material is can withstand that conditions or not, right? So you have to assess, right? Therefore, when you screen the materials for a specific application, you have to know about all the requirements for that specific application, right? So I told you, when it comes to material, there are thousands of material, right? So it is easy for us to, if we have a certain material classification method. So let's see the ways that we can classify the material, how we group certain materials together, right? We'll see, right? There's one common way we can classify the material according to its general properties, right? We can say it's a metal or a non-metal, right? We can say it is a metal or a non-metal. If it is a metal, for example, iron, aluminium, copper, zinc, lead, all those are metals, right? Again, we can classify those metals as ferrous or non-ferrous metals, right? Ferrous or non-ferrous metal, like that, right? So depending on the carbon content, we can classify like that. So this is just a way of classifying the material, metals or non-metals, right? If it is a non-metal, it can be rubber, asbestos, leather, plastic, glass, like that, right? We can group. We can say iron, aluminium, copper, zinc, lead, and those things are metals. These are non-metals, like that. This is the simple way of classifying materials, right? So another way is according to the nature of materials, right? For example, metals and alloys in one group, ceramics and glasses in one group, like that, right? Copper, cast iron, alloy steels, we can group together, right? So window glasses, right? Also those kind of refractories, those things you can group together, right? So this is another way, right? Again, we can group into polymers according to the nature of material, semiconductors, composites, like that, right? So likewise, basically, we can classify material oils like this. We can classify the material as metals, ceramics, polymers, or as composites. Composite means that material contain more than one of these materials. Sometimes it is a combination of ceramics and metals, right? So we call composites, right? This is another simple way of classifying materials, right? So this is another way, according to the most important function they perform. For example, that means earlier we say metals, non-metals, like that. But Here we consider the function of the material. For example, structural materials, optical materials, right? Biomedical materials, right? If it is a structural materials, so we can combine steels, aluminum alloys, concrete, fiberglass, plastic, wood into one group. So function is as a structural materials, right? So if it is optical materials, we can group silicon oxide, gallium arsenide, glasses, aluminum oxide as a one group. So this is depending on their function, right? So this is a simple, I explain you 3 ways of classifying the material, right? So you don't have to memorize all these things, right? This is just to explain the way of possible ways of classifying materials, right? So I told you earlier, the structure of a material greatly affect the properties of material, right? So the structure of a material, if we say structure, we can define the structure of material at different stages. At initial stage, we can say the atomic structure of material, right? That means how the atoms are arranged in a material. So atoms are very small, right? So we consider the very small atoms and how they have arranged and how that arrangement affect the properties of material, right? So this is one way of describing a properties of material based on the structure of a material, right? Then this is another way of describing a structure of a material, that is how those atoms that we told here are arranged in short and long range order. That means we call atomic arrangement, right? That means we can divide that into amorphous material or crystalline materials, right? Right? If the atoms are arranged in an orderly way in a short distance, that we call amorphous material. If the atoms are arranged in an orderly manner in a long distance, we call crystalline material. Right? I hope you will learn those things in your chemistry course. Right? So here the amorphous material means short range atomic arrangement. The atoms or ions show a particular order only over relatively short distances. Right? This Armstrong means a way of measuring the distance. This is equal to 10 to the power minus 10 meter. 1 Armstrong is equal to 1 into 10 to the power minus 10 meter. This is a way of measuring the distance. You know, when it comes to the units of measurement, we have kilometers, we have meters, we have centimeter, we have millimeters, we have micrometer, right? Then we have nanometer, then we have Armstrong, right? This is a unit we use to measure short distances. So amorphous material, they have a short range atomic arrangement, right? The crystalline material, the atoms, that means what is atom? You know the Sinhala meaning? Paramanu, right? In a crystalline material, long range atomic order is there. That means atoms are arranged not in short distances. 1 to 10 nanometer Armstrong is for amorphous. 10 to centimeter scale is for crystalline material. This nanometer is again a unit that we use to measure the distances. I hope you know, right? 1 nanometer is equal to 10 to the power minus 9 meters. Okay, so this is one way of describing the structure of a material. We can say it is a amorphous material or a crystalline materials based on their way of atomic arrangement. Right? So the third one, we talk about atomic structure. Right? In an atom, there are electrons, protons, neutron. Right? Then atomic arrangement, that is amorphous or crystalline material. Then the nanostructure. We describe certain material considering their properties in a range of 1 to 100 nanometer scale. Right? Then microstructure. That means we describe the grain sizes of a particular material. Macrostructure. That means we consider a piece of material that has length greater than 100, around 100 micrometer, and describe their properties. So that is the macrostructure. Right? So we can describe certain properties, material properties, considering its macrostructure. Certain properties considering its microstructure. Certain properties considering its atomic structure. Right? So that's why we should learn how to describe the atomic structure. So you know, in the atomic structure, in atomic level, you have electrons. Then you have protons, right? You have neutrons. There is a nucleus, right? Electrical charge, the atomic number, right? Those things I think you have already learned in your A levels, right? Protons and neutrons are in the nucleus, right? Electrons are in the shells around the nucleus, right? The charge of an electron is this amount, right? So atomic number means the number of proton in an atom, right? Those things I hope you have already learned. So what is atomic mass? Because these things you will need when you go further in this course. Atomic mass, we use the symbol capital M to represent atomic mass. The mass in grams of the Avogadro constant of atoms. Avogadro constant means 6.022 into 10 to the power 23 atoms. The weight of this amount of atoms in grams we call atomic mass. Right? Atomic mass, the unit grams per mole. Okay. So I will describe this example in the next recording. Okay, let's do example to identify atomic mass, Avogadro number of a element. Okay. So this example asks you to calculate the number of atoms in 100 gram of silver. Right? Silver is a metal. Calculate the number of atoms in 100 grams of silver. How you do that? You have given one information. Atomic mass of silver is 107.868 grams per mole. So how you find the number of atoms? Can you think? 1 mole is an Avogadro number of atoms. What is Avogadro number? 6.022 into 10 to the power 23. So in 1 mole, you have Avogadro number of atoms. If you can find how many moles are in 100 gram of silver, then you can find the atoms, number of atoms in 100 gram of silver. Right? This is the solution. Right? First step is to find the amount of silver mole in 100 gram of silver. Mole means a mauleka, right? Mauleka, maula gram 100ක silver maula කොච්චරක් තියනවද? එතකොට අපි කරන්නේ, what we do is we divide the 100 gram by the atomic mass. Atomic mass is weight of 1 mole. That means weight of Avogadro number of atoms, right? So if you divide 100 by 107.8868, you will get the number of silver mole in 100 gram. So to find the number of atoms, what you do? 1 mole is Avogadro number of atoms. This 16.022 into 10 to the power 23 is the Avogadro number. In 1 mole, this amount of atoms are there. Then in this much of mole, that means this much of mole, how many atoms? So you multiply it by this one. So you will receive 5.58 into 10 to the power 23 atoms as the number of atoms in 100 gram of silver. Right? So this example is for you to understand the atomic number, atomic mass, mole, and Avogadro number. Right? So I hope that you already know about the periodic table, right? So it has grouped certain materials with similar properties in this column. With these rows, the properties of materials change, right? Here you have the gases like helium, neon, argon, right? Here you have metals in 1A, right? Here you have metals, right? So in between, here boron, gallium, right? Those things, the semiconductors, silicon, right? Those things in here, carbon, polymer materials, right? So you can identify different group of materials, elements in the periodic table, right? So this gives you very important information, the atomic number, the atomic mass you can get from this table as well, right? So here you see the alkali metals in the 1A column, right? Alkaline earth metals in this one, alkaline earth metals, right? The transition metals, the yellow color ones, right? Then basic metals, aluminium, right? Gallium, right? Lead, tin, those things. Then non-metals, carbon, nitrogen, oxygen, right? Sulfur, phosphorus, the non-metals, right? Then halogen is this column, right? 7A, we call the halogens, right? Then the noble gases, here this column, the 8A column, and we call noble gases, right? You can identify by the color, right? It's easy to understand, right? So these are elements, right? The pure elements, right? So in an element, you know, the element is constructed from the atoms, right? In an atom, we can describe its electronic structure. That means in an atom, how the electrons are arranged around its nucleus, right? So you know there is a development of the describing the ways of electronic structure of atom, right? So some people initially describe it as like this. We call the Bohr atomic model, this one. So here you have nucleus, then here you have, we call orbits, right? Then you have electrons in the orbits, right? So these are specific locations. right? So now we use the electronic structure to express how the electrons are located around the nucleus. We say they are in the specific energy levels around the nucleus, right? So we say those energy level, the quantum levels, right? So we have different energy levels like 1s, 2s, 2p, like those are we call the energy levels, right? I hope you have learned these things in your A levels also, right? So these energy levels right here, 1s, 2s, 2p, right? 3s, 3p, 3d, like that. But when they fill, when the electrons fill in these energy level, there is a order, right? It's like, it's not like the electrons fill in 3s energy level, then 3p energy level, then 3d energy level, then 4s energy level, like that. There is a different way of filling the electrons around the nucleus, right? This we call this Aufbau principle, right? So first it fill the electrons occupy in 1s level, right? I'm talking about uh, an atom that having large number of electrons, right? Then first electron in the 1s level, right? Then from here to here, then in the 2s level, right? Then 2p level, then 3s level, then 3p level, then not 3d level but 4s level. After filling 4s energy level, then it fill the 3d energy level, then 4p energy level, then 5s energy level, then only 4d energy level, like that, right? I hope you know these things, right? So we'll see uh, this example of for neon. So write the electronic structure of neon. Atomic number is 10. How you write it? Here, first, in this uh, S energy level, there can be 2 electrons in S energy levels. In P energy levels, there can be 6 electrons. Right? In D energy level, there can be 10 electrons, like that. So neon has electron atomic number 10. That means it has 10 electrons in an atom, right? So 10 means 2 go here, 2 go here. Then you have remaining 6. So remaining 6 in 2p level. So you write it like 1s2, 2s2, 2p, 6. That is how you write it, right? So if I write it in this one, I will write it like this. No. It can be write like this, right? In S level, energy level, there can be maximum 2 electrons, so you fill maximum 2. In 2s energy level, there can be 2 electrons, so there is 2. So here there can be 6 electrons, so it's filled. This 2 plus 2 plus 6 is the 10, that means number of electrons in neon, right? So this is the answer, right? So can you try to write the electronic structure of iron? The atomic number is 26, that means there are 26 electrons in its atom, right? You follow this principle and you try to write the electronic structure by your own for the iron, okay? So that's about writing the electronic structure. So often when you go further in this course, you will find the term valence. What is the valence? The valence of an atom is the number of electrons in an atom that participate in bonding or chemical reactions. Usually, the valence is the number of electrons in the outer S and P energy levels. Right? Usually, valence is the number of electrons in the outer S and P energy levels. Right? That means not all the electrons in an element can participate for to form the bonds. Right? Because elements cannot stand as elements, so they make bonds to stabilize, right? So not all the electrons in the material can participate for a bonding, but the outer S and P energy level electrons can participate, right? For example, if you write the electronic structure of magnesium, it will be 1s2, 2s2, 2p6 and 3s2, right? So outer shell is, because 1 means the shell number, 2 is the energy level number, 2 energy. So this is the outer shell, right? So there are 2 electrons in the outer energy level. So we say the valence is 2 for magnesium, right? If you take aluminium, that means electronic structure you can write like this. So outer energy level, there are S and P energy levels. So 2 plus 1, we call valence is 3. For silicon, outer energy level 3s2, 3p2, the valence is 4. 2 plus 2. Actually, the meaning is here other than the energy level 3, other than this S shell, there are other 3s, 3p and 3d, but they are not filled. Right? So these electrons they are not stabilized electrons. So they can participate in bonding with other materials of the same element. Right? So that's why we call those are valence electrons. Right? So it's like that. Right? But this is not true for every case. You will see when we talk about the transition metals, right? Sometimes we cannot express their valence like the sum of S and P energy level electrons like that. Okay. So the atomic stability and electronegativity. What is electronegativity and atomic stability? Actually, we describe the electronegativity as a way of becoming stable, right? That means electronegativity describes the tendency of an atom to gain an electron and become stabilized, right? So if some element prefer to get the electron from outside and become stable, so we call that is a electronegative material. Not all the elements can take electron. Some prefer to give electrons to some other element to become stable. Some like to get an electron to become stable. So electronegative materials prefer to gain electrons and become stable. Right. Now, I told you elements cannot stay as elements. they make bonds with the same element or different element to become stable, right? Usually we talk about 4 types of bonds in this course, right? One we call a metallic bond. Another we call a covalent bond. Next one is ionic bond. Last one we call van der Waals bonds. Right? Let's see one by one. Right? So what is a metallic bond? It happens in metals. If an element has a metallic bond, they are good electrical conductors and they have good ductility. Right? Or maybe I will describe these 4 types of bonds in the last recording. Okay. When you study about materials, you will encounter basically 4 types of atomic bonds, right? Because of the type of bonding, their properties can change, right? So basically there are 4 types of bonds. 1, metallic bonds. 2, covalent bond. 3, ionic bonds. 4, van der Waals bonds. We'll see one by one what it is. Right? So in most of the metals, you can see this metallic bond. Right? So what happens is, in metals, there are valence electrons in their outer shell. So they release those 2 outer shell electrons to become stable and they form a sea of electrons. If every atom in a metal release those valence electrons, there will be a sea of electron around the nucleus of the metal. Right? So then once originally the atom has equal number of protons and equal number of electrons, right? Once you release electrons, your nucleus become positive charge, right? So those positive charged atom nuclei will held together through these released electrons. Those released electrons are not only for a particular nucleus. They are shared with several other nucleus. So in that case, we are saying these positive charged nucleus are in sea of electrons. So as a result, the metals exhibit very good electrical conductivity properties at relatively low temperatures, right? Because of this sea of electrons, right? So you see these interactions between electrons and the nucleus are not directional, right? They are randomly around this positive charge nucleus. So in that case, they have good ductile properties. What is ductility? Ductile means what? We can stretch those metals into a very good extent without breaking it. We call it ductile. So because of this non-directional nature of this electron, this metallic bond, right, they exhibit good ductile properties. So you see how, depending on the type of bond, right, these properties of metal become specific to them, right? So this is about the metallic bond. Right? Let's see about the covalent bond. I'm sure you have heard about covalent bond, right? That means if one atom has valence electron, it share their valence electron with some other atom to become stable, because they always try to fill their outer energy shell to become stable. In that case, they share their valence electron with other atoms. For example, you can see this silicon atom. In its outer shell, it has 4 electrons, right? So it will be in a stable position if this contain 8 electrons in the outer shell. So what will it do is it share 1 electron with some other silicon atom. Likewise, it share this 4 electron with 4 silicon atoms. Then it will receive 1 electron, 1 shared electron from 4 silicon atoms. So such type of valence electron sharing we call a covalent bond, right? So you see this bond is directional, we call, which means it cannot like very free like in metallic bonds, right? So we call these are directional bonds, so therefore they are very strong. The bonding is quite strong, right? So this is how a covalent bond can form, right? Then the third one we call the ionic bond. Then there what happen is, let's think about sodium chloride, right? So in sodium atom, there is 1 valence electron in its outer shell. It preferred to give it to another atom to become stable, right? In chlorine, in its outer shell, it has how many electrons? 7 electrons. If it have 1 more, then it is a stable condition, right? So in that case, chlorine accepts that electron from sodium, right? So then sodium, if it give completely 1 electron away, it will have positive charge. This sodium we call, now it is sodium ion, right? Once chlorine receive that electron, it will have net negative charge. We call chlorine ion, right? The atom who donate the electron we call the cation. That is, sodium is the cation, right? The atom which receive the electron we call anion. Then chlorine is the anion. So this type of electron transfer and the bond we call the ionic bond, right? It is the ionic bond. This is example, right? So next one we call van der Waals bonds. There are no electron sharing or release of electron, such thing in van der Waals bonds. What happens is, if there is a neutral atom, that means without having any valence electrons, right? When it reach another similar atom, there will be a polarization we call. That means because another atom reach this atom, right? This atom, so it will become like this. This side will have negative charge, this side will have positive charge. So we call these are polarized atoms, right? So because of this polarization, it can have this type of attractions we call van der Waals bonds. They are very weak bonds, right? So these are basically the 4 types of bonds. If you need more information about this bond, right, different types of bond, you can refer the chapter 2 in the reference book I uploaded to LMS. Right. So I hope very much that we will be able to do a Zoom lecture next week if there were if there are no any scheduled shifting works, right? So, and also I hope to see you all personally, uh, physically in university very soon. Right? If you have any question, you can simply send an email to me. Right? So I recommend you to read the reference book I gave you, so you can get more information than I delivered to you from this lecture. Right? Okay, thank you very much. Anyway, I will try to record a new one. Otherwise, for those who couldn't join the lecture, I think they will have a problem, right? Because I think I lost the previous recording also because of the sudden power failure. Right? We'll see. Right? So a steep slope indicate necessity for high forces to separate the atoms and cause the material to stretch elastically. Right? So if the one material have a steep slope compared to the material which holds, it has high modulus of elasticity. That means high slope. Right? Modulus of elasticity are typically higher for high melting point material. High melting point means what? You have to provide more energy to melt it. That means their binding energies are high, right? So they usually exhibit high modulus of elasticity, right? Then in metallic materials, the modulus of elasticity is dominated by the stiffness of the atomic bonds and considered as microstructure insensitive, right? Remember we talk about that atomic structure, microstructure, macrostructure in the first lecture, right? In metallic materials, it says that modulus of elasticity is governed by the stiffness of the atomic bonds, right? But for materials like ceramics, right, the Young's modulus is dependent on the amount of porosity. That means how many pores are there, right? If less porous, this can change like that, right? So this is about this is some information about the Young's modulus and characteristic of Young's modulus in a few materials, right? So please give me 1 minute, okay? Okay. Here you can see what I explained earlier, right? So this is how we can relate. This column is the Young's modulus value for few materials, for metals, right? So here is the melting point, right? This describe what I explained earlier, right? You see, um, here the melting point. Some materials, they have high melting points. For example, if you move from magnesium to copper to iron, right, then the melting point increases. The similar way, the Young's modulus increases, right? Young's modulus increases. On the other hand, if you check the variation of Poisson's ratio, it shows a reduction. That means what? That means it's hard to stretch. Poisson's ratio means roughly we can say that, right? So I told you that how steep the slope of a stress strain curve give certain indication about their Young's modulus. For example, slope of steel, right? The slope of steel is higher than slope of aluminium. In engineering, a stress strain curve, which means steel have high Young's modulus compared to aluminium, like that, right? Those are general characteristics, right? So I already explained about that elastic strain, right? I will add a new term, the plastic strain. Elastic strain means the fully recoverable strain. That means once you apply a load, it will stretch. Once you release it, it will become to its original size and shape, right? That we call the elastic strain. But plastic strain, we call there will be permanent deformations. That elongation or contraction, they are permanent, right? When the stress is removed, the material does not go back to its original shape. That's what we call the plastic strain, right? So far we talk about linear elastic materials. But there are materials we call non-linear elastic materials, which means the elastic materials we earlier discussed, they have linear relationship between a stress and a strain. For example, like this, right? This part, it shows the linear relationship between a stress and a strain, right? But there are material that they doesn't show that type of linear relationship, but still they are elastic material. We call non-linear elastic material, right? Only difference is this slope is not linear. In that case, we define their slope at specific points. For example, if you need to find the slope at this stress level, you put a tangent to the curve at that point and you get the slope of the tangent, right? So the slope change, right? Depending on the level of stress, the slope change and the Young's modulus, that means slope, it varies. Right? So we don't define one certain value for modulus of elasticity for such materials. We define it for a particular point, at a stress point, the slope. Right? This is for non-linear elastic materials. Okay. Now we will identify some other types of materials that will behave differently from linear elastic material and non-linear elastic material and plastic materials, right? So those we call viscous material, right? So earlier when you apply a force, the strain develop at the moment, instantaneously, right? But in viscous material, once you apply the strain doesn't develop very quickly. The strain develop over a time period, and it is not in phase with the applied stress. Let's say you apply 10 Newton, then there will be certain strain at that 10 Newton, but that strain keep changing. That means a strain develop over time. That type of material we call viscous materials, right? Viscous materials, they does not return to its original shape when the stress is removed, right? It will keep remain deformed, right? Mostly some viscous fluids. Yeah, sure. I will upload to the recording and the PDF to the lecture, right? This is not difficult, no, right? Are these things difficult? You just have to remember, okay, right? So the material will remain deformed when the stress is removed. So what are the characteristics of viscous materials? One thing is strain development is not in phase with the applied stress, right? Material will remain deformed when the stress is removed. That means it's not behave as elastic material, right? Okay. Viscoelastic material. What is that? We use viscoelastic material for the polymers, but same meaning, but we use it as anelastic material for metals, right? So viscoelastic mean what's the just meaning? Viscous and elastic. Then it may have the properties of elastic material and the viscous material. That's what we call viscoelastic material, right? So in there, the development of permanent strain is similar to the viscous material, but part of the strain developed will recover over a period of time when the applied stress is removed. That means there will be permanent deformations, but once you remove the applied stress, some amount of strain again will recover. That means, let's say it elongates 2 millimeter, a permanent deformation. But once you release the force, let's say 0.5 millimeter, strain reduced over some time, right? So such behavior we call viscoelastic materials. Okay. So a strain rate is very important term, right? Because the strain of a material is depend on how fast you apply the load, right? How fast you apply the load. So strain rate means the rate at which the strain is developed in a material, right? Many material considered to be ductile behaves as brittle when the strain rates are high. That means in some materials, the strain development is quite fast, right? So in that case, even the material is ductile, it can behave as brittle material. Ductile means what? Ductile material. That means it can undergo large plastic deformations. We call ductile materials, right? Even a ductile material can behave as brittle. Brittle means what? Brittle means easily can break. Easily like glass. Glass is a brittle material, right? If the strain development is quite high, then even a ductile material can behave as a brittle material, right? So this is about a strain rate, right? Now we will talk about the tensile test, right? We talk about that plotting a stress strain curve, right? We talked about tensile stress, compressive stress, all those things, right? So how we get the information to plot such graph, to plot a stress strain graph like this. Uh, let's say this type of graph, right? This is only a part of the graph. How you get the information? This graph shows the variation of stress and strain. How you get the information? We get that information for a particular material by conducting a, we call a tensile test, right? Tensile test measures the resistance of a material to static or slowly applying forces, right? What we do in here is we have a standard size, we call this a specimen. It has a, we call this a gauge length, usually 2 inch, right? It has a fixed diameter, right? So the machine has, we call the universal testing machine, right? You can test the material's tensile strength and compressive strength both using a universal testing machine, right? You keep this specimen in here and you apply a force. You slowly increase the applying force and you measure this length, change of this length. We call this change of the gauge length. By conducting this type of test, we can get two information. One, we can measure the applied force. The machine provides the facility to measure the applied force. Then by measuring this length for each load increment, you can get the change in length. Those two information you can get, and we'll see how you convert those information to plot the stress strain curve, right? So actually we have in our university benchtop tensile testing machine. We call not a universal testing machine, right? It is a benchtop tensometer. In there we use a flat specimen. That mechanism is same, but we use small specimens, right? So if you are in faculty, definitely you will get a chance to do a practical on how to conduct a tensile test. But unfortunately, since you are unable to come to the faculty to do that experiment, I'm not sure whether you will be able to do it before you finish this course, right? I will try to give you a demonstration video by asking some our demonstrator to show how to operate it, or else I will give you a set of data that we obtain using that machine, and you can use those data to plot a stress strain curve and get the experience, right? So if you are interested, you can search in YouTube the tensile test. It will show details about how to conduct a tensile test, most probably not using that benchtop machine, but using a universal testing machine, right? So I told you initially we have a specimen, right? We consider this as the length of a specimen because under the applied load, right, the break of this specimen will happen at the weakest cross section. That means minimum cross section locations, right? So we know the initial diameter and the initial length of the specimen, right? So I told you we can get the applied load F and corresponding change of length from the tensile test, right? So we convert this force and change in length that we obtain in that tensile test to calculate S and E. Here we call this S as engineering stress. We call actually not, this is a stress, okay, this is wrong. This should be, this is E, we call engineering strain, not stress, right? Engineering strain, right? So to plot the engineering stress curve, we always use the original cross section of the specimen and the original length of the specimen. You know, with the application of load, this cross section change. It's not same, but to plot this curve, we use always the original cross section and original length. That's why we call this curve engineering stress strain curve, right? So this is typical for a metal, this type of shape. Once you get the data of force and change in length and plot it, you will get this kind of, this is the graph, okay? This is the graph, right? So you can use this graph to identify very special features or very special characteristics of a particular material, right? So we will go for one by one, right? So here you will start loading. You convert it to stress and strain. When you keep the loading increase, that means you increase the stress, then you will have a linear region like this, right? After certain stress level, this graph going to be curve. That means at this linear region, they often show elastic behaviors. But after this point, at this area, it start to show elastic and plastic behavior. That means after this stress level, right? If you keep increase the stress, and once you remove this stress, it will not become to its original shape. That means after this point, the material will behave as a plastic material, right? So how this point we call the yield point. The stress we call yield strength, right? So this the definition of yield strength, the point where the material yields to the applied load and start to show the both elastic and plastic deformations. After this point, the material behaves as a plastic material, right? So how you identify this point and the yield strength? What you can do is we use a method. We call this value corresponding to here yield strength or 2% yield strength. That means once you plot the curve, you select 2% of a strain value. That means 0.002 strain point in this axis. This is the 0.002 strain point. Then you draw a line parallel to this linear part. You draw a line across this 0.002 strain point parallel to this linear path. So you extend that line, and when it touches the curve, that point we call the yield strength or 2% yield strength. And this region we call elastic region. Right? This region we call elastic region. Right? So now you keep on increasing the applied stress. Right? So when you apply the stress, right, then this part under these stress levels, it show plastic deformations, right? So at this point, the material will start necking. That means it show a visible reduction of cross section like this. I'm not sure if you can see this clearly. There's a reduction in cross section. It's visible. So the point where it shows this necking, this one we call necking, we call the tensile strength of the material. That is the maximum stress of the engineering stress strain curve. If somebody asks you to find the tensile strength from a graph like this, if you get the maximum point of the stress strain curve, then it is the tensile strength. Right? So at this point, the necking will start, and when you further increase the load, it will break at this point. We call a fraction. Right? So this area we call the plastic zone, the plastic region. Right? So you can identify regions in this type of engineering stress curve: elastic zone, plastic zone, then yield strength, right? Yield strength value, the tensile strength, those things you can identify. Right? Okay. Now here is the example, right? If you can remember the things I explained here, can you try this example? If you need, I will can put the graph here for you to check. Right? A force of 100 Newton, 100 kilonewton is applied to an iron bar with a cross-sectional area of this size, and having a yield strength of 400 megapascal and a tensile strength of 480 megapascal. Determine whether the bar will plastically deform and whether the bar will experience necking. So now we are dealing with stresses. If they were given a force, you have to first convert into the applied stress. Right? Applied force is 100,000, cross section 10 into 20 millimeter. Right? So you once you calculate the applied stress, it will come as 500 megapascal. The applied stress. So the informations were given to you: yield strength 400, tensile strength 480. First question will see, determine whether the bar will plastically deform. What is the requirement for plastically deform? If the applied stress is exceed the yield strength, that means bar will plastically deform. What you have to do? You have to check the applied stress with the yield strength, whether the applied stress is greater than yield stress or less than yield stress. Right? Your applied stress is 500. Yield stress is 400. In that case, applied stress is higher than the yield stress. So you are somewhere here. In that case, the bar will plastically deform. because applied stress is higher than the yield strength. The next question, whether the bar will experience necking. Necking will happen when the applied stress exceeds the tensile stress. Right? The tensile strength is 480, applied stress is 500. So applied stress is higher than the tensile stress. In that case, bar will experience necking. That's how we come to conclusions. Right? Is this part clear? So I have given you the answer in the next slide. Okay, so I have included one more example, right? So you can, it is from this part, this engineering stress curve part. So you can try it at home, right? So I left you two examples, one on that Young's modulus relationship, another one on the engineering stress strain curve, right? So you can try those two examples at home. And if you have any questions, you can ask during the next lecture. Right? So I will be, I will be uploading this one and this recording. I'm not sure whether I have that previous recording with me because I lost the power. I will check. If not, I will again record one and upload it to you. Right? So this is all I planned for today. Right? So if you have any question, you can ask now. If not, we can stop for today, right? You can look for that PDF and the recording by around 2 p.m. Okay. Okay. If you don't have any question, I will end the meeting. Okay. Thanks for coming, and we'll see. It's not difficult, right? Some says it's too difficult. Those are basic things. Next time you come and you ask me what the difficult, I will explain. That is no problem. Right? Not very difficult things because I just teach you about this strength and elasticity, plasticity, those things. I haven't used many equations and anything. Right? So please go through again. I am sure it's not very difficult. All the informations are in the slides, right? So you can directly refer the that textbook I uploaded. It contains more information if you need, right? So those who feel that this is difficult, please refer the book also, right? So I will end the meeting for today and thank you for your participation. Can we do that practical after university? Actually, you can, because I can include it in another course I will be doing in that in a few future courses. Doesn't matter, right? I will definitely let you do an exercise and I will show you a video on how to use the apparatus. But I know it's not enough because practical is a practical, right? You should be there and you should operate and see the difficulties. If there are anything you cannot understand, you should learn the equipment like that. No, so it's practical. So we'll try. I try my best after university starts to schedule that one for you. Right? The equipment is in our university, so it doesn't matter. Okay. So I will end the meeting for today and thank you for your participation. I hope you all will come for the next lecture as well, because in your senior badges, the amount of participants become less and less with time. Right? Don't do that. And I hope you all come for the next lecture as well. Right? So thank you very much.
Thank you, madam.